Hello everyone. Our presentation is on acoustic source localization using a data-driven approach. Acoustic source localization, put simply, is a method of locating a sound source or broadly gleaning information about the sound source by processing acoustic signals. Its applications span a wide variety of fields. Some of them are shown here. The conventional source localization techniques like acoustic beamforming suffer from spatial aliasing and poor resolution at lower source frequencies. Due to rapid growth in computational power, deep learning algorithms have emerged as powerful tools due to their ability to learn patterns from data in any shape or form. So, to overcome the limitations of conventional techniques, a convolutional neural network has been developed as a proof of concept to locate and track static and moving sound sources. A neural network needs data from which it can learn. This data is synthetically generated. Analytically defined monopole sources are simulated randomly across the scanning grid. The pressure signals radiated by the sources are recorded by a virtual microphone array in the shape of a logarithmic spiral. This shape is chosen so as to ensure good performance over a range of frequencies. The pressure signal from a source S on the scanning grid to a microphone M on the array plane is given by equation 1, where Rs is the distance between the source and the microphone, and C0 is the speed of sound in air. Pressure signals from each source are added at each microphone to generate the pressure vector P, which is given by equation 2. The cross-spectral matrix is defined as the pressure vector times its complex conjugate and is used as an input to the CNN. The network's prediction is compared against the ground truth, which contains the actual source location data from which the cross-spectral matrix has been derived. A convolutional neural network takes an image for its input, which in this case is the cross-spectral matrix. The convolution layer applies a series of filters to it that help the network capture the high-level features of the image. The pooling layer then reduces the dimensions of the image while preserving the dominant features. The image is then flattened and fed to a regular neural network. The network compares its predictions against the ground truth, calculates the loss through a loss function, and adjusts its parameters so as to minimize the loss. Results for a particular case, 6 sources at 8000 Hz spread randomly over a 12 by 12 scanning grid are shown here. The CNN managed to locate all the 6 sources perfectly. Multiple such models were developed to study the performance over a range of frequencies. The predictions were far more accurate and of much better resolution compared to the beamforming output, and even more so at lower frequencies. To conclude, the results show much promise, and it is expected that with more data and training, a robust and generalized deep learning framework for detection of acoustic sources in real life applications can be successfully built. Thank you.